All right, now we're looking at section 2, which is interpreting the evidence for change over time. There is a variety of evidence we see in a variety of different ways. We're just going to have a general look at what we see and observe. So the first we're going to look at are the three kind of old types of evidence. These we've been observing for a long time. That is fossils, and everybody should be very familiar with them. Patterns of early development, as in when the organism is conceived up to when it's a couple weeks old in the womb. And then similarities in body structure. You've probably noticed that many animals have similar structures. So we'll look at how they inherited those from a common ancestor. Then there's a couple modern types, which we'll add on, which is DNA sequence and protein structure, as in how the proteins are put together from amino acids. So we'll start going through these one at a time, and first we're going to start with fossils. Now, of course, fossils show how organisms have changed over time. Now, we look at the fossil record and we see, at least in the recent last 65 million years, organisms that are very similar to the ones we have today. We find the modern sloth is very much similar to the giant sloth, of course, except in size. We had giant cave bear in the past, which is clearly related to our modern bear. We've seen saber-toothed cats in the fossil record, which are clearly related to our modern cats. And in modern times, like in the last 2 years, they've been pulling out fossils of feathered dinosaurs that are about to seal the link between dinosaurs and birds. So dinosaurs would have been the common ancestor between bird species. So we see these kind of things in the fossil record, and it shows us that animals have definitely changed over time. And these animals, of course, some of them have gone extinct because they were no longer well adapted to their environment. They had to change, and their changed, adapted form is what we still have with us here today. Then we go on and look at early development. This one was kind of hard to understand, but just know that if we have related organisms, such as a wolf and a coyote and a fox, and we look at how they develop in the womb, if they're closely related, they'll have very similar developments. They'll look the same as a fetus if they're closely related. But if we compare, say, a chicken, a fruit fly, and a sea urchin, and we could throw a couple other weird ones in there, like a hagfish or something like that, we'll see that these guys have very, very different patterns of development because they are not evolutionarily related. Now, of course, it's important to know that when I say related in these talks, I'm not talking about first cousin or second cousin or brother, father, son, that type of thing. I'm talking about related as in millions of years ago, they shared a common ancestor. So, related in the text that we're talking about now, in evolutionary context, is not an immediate relation, but a very, very distant relationship going back millions of years. So that's important to remember. Then we get to body structures, and this is a really neat area. We talk about homologous structures, and we find this in many land-walking creatures that share a common ancestor. For instance, we have a humerus, that's your funny bone or your arm bone, a radius and ulna, those are your bones of your forearm, your carpals, metacarpals, and phalanges, which make up the bones of your wrist, your hand, and your fingers. We find these same bones in the same arrangement in many, many different organisms, from dolphins to whales, cats and dogs, horses, and other land-walking creatures. These homologous structures indicate that we inherited these from a common ancestor, very, very distant common ancestor. So a homologous structure, down here, are the parts that are shared by creatures with a common ancestor, even if they do a different job. The bird and the bat and the dolphin all have the same arrangement of arm bones that we all share, but they have done very different things with it based on their needs in the environment. The bird has adapted them to fly like the bat has. The dolphin has adapted it to swim very well, whereas we have adapted it for advanced manipulation of objects, picking up things and holding things. Next will be similarities in DNA. And this is widely considered the best evidence because it shows us letter for letter, gene for gene, exactly how related or how different every organism is from every other. It shows, well, of course, we combine this with our other evidence. It just doesn't stand alone, and usually this agrees with the other evidence, but usually DNA evidence will be used to disprove, say, mistakes we've made in the past, like the relatedness between the elephant shrew and the modern elephant. So the DNA shows the exact genes we inherited from our ancestors and exactly how they've changed, which mutations they picked up as organisms changed from giant sloth into regular sloth, and of course the mutations they may have picked up as they changed to other organisms. So it makes the new form of the organism with those mutations, and we can see exactly what's happened to them as they changed. Now, similarities in protein is very similar, because protein is made from the instructions in the DNA. This is probably the second best way of determining species relationships. Since it's made from the instructions in the DNA, it's almost as good as looking at species relationships. The order of the amino acids that are put together in the protein will be slightly different between proteins and different organisms. So I could take a fingernail clipping from me, a little bit of horse hoof, say the horn of a goat, and other things similar from other organisms, say a dog toenail versus cat claw, and compare those in their amino acid structure and see where the amino acids vary and how these organisms have varied. Or we could compare the hairs of, say, a boar, which has very stiff hair, to a rabbit, to a dog, to a chinchilla. Of course, you can feel the difference in these hairs, and you will be able to see the difference in the protein structure if we compare the proteins of these different types of animals' proteins in their hair. Now, the next part is typed because it's in class and couldn't be writing this on the board at the time, but a branching tree, it's just basically a family tree that shows how different species are related. So a family tree would show differences or inheritance between, generations of humans. A branching tree is showing relatedness between species that will go over millions of years. So it's like a family tree, but we're spanning millions of years, and it's showing relationships in individuals. We're actually showing relationships between species, whole groups of individuals that interbreed. Now, how species form is a pretty easy idea. Isolation is the most important part in forming a new species. You got to take a species, split it into two groups that are separated and can no longer interbreed. This has to be a good separation, not just a road dividing the groups, because you can crawl across a road. A lot of animals can crawl under a fence. But if it's something like a river for animals that cannot swim, that could be sufficient isolation for them to start becoming different. Over this long period of time, one group will get certain mutations, the other group will get different mutations, they'll change their appearance, they may adapt in different ways, and over time they'll be so different, these two different groups, that they'll no longer be the same species. One group may not be able to mate with the other group successfully, even if they are willing to mate with the other group, but often they may become so different that one group does not recognize the other group as being related to them anymore. They look too different, so they are not willing to mate with this new group. So we can have both situations arise when we are forming a new species. So they must stay isolated completely for a long time. We cannot have any genes moving from one side to the other. If we're sharing those mutations, it's going to increase the sameness of the two species, and they will not keep getting different. So they cannot have individuals moving from one group to the other sharing their genes. Next, here very soon, we'll look at the fossil record, which is very interesting. And this is the end of section 2.